Welcome to a lesson on line integrals of vector fields. More specifically, we'll determine the work done by a vector field. To determine work in a straight line, we can dot the force and displacement vectors. However, if the path is not in a straight line, we could break up the path into smaller and smaller pieces, and the accumulation of these increments of work give us an infinite limit of the change in f and the change in d, which leads to the line integral of the force field dotted with differential r along the curve C. And to integrate this in terms of t, we can rewrite differential r as r prime of t dt, and then we can rewrite the vector field f as a vector field in terms of t using the x, y, and z components of our vector valued function r of t for the path of the line integral. And we can also express work as a line integral of the force field dotted with the unit tangent vector integrated with respect to s, where f dotted with t represents the increment of force and ds represents a small change in arc length. But for this video, we're going to use this form here. Let's take a look at our first example. We want to determine the work done by the force field represented by the vector field f of xy equals negative y comma x along y equals x squared minus 2 from the point 0, negative 2 to the point 2, 2. I've sketched our path of integration here. Here's the point 0, negative 2, and here's the point 2, 2 along the curve y equals x squared minus 2. So our first step is to write our path of integration as a vector valued function r of t. So if we let x equal t, and since the equation of this path is y equals x squared minus 2, we could let the y component equal t squared minus 2. And the interval for t would be from 0 to 2. Let's go ahead and set up our def integral in terms of t. Limits of integration will be from 0 to 2. We'll rewrite our vector field as a function of t using x of t and y of t. So the x component will be the opposite of y of t. Well, here's y of t, so instead of t squared minus 2, it'll be 2 minus t squared. For the y component is equal to x of t is equal to t. And we'll dot this with r prime of t, so we'll have 1 and 2t. Let's go ahead and evaluate this on the next page. So we'll have 2 minus t squared times 1, that's 2 minus t squared, plus t times 2t, that'll be 2t squared. Let's go and combine our like terms. We'll have 2 plus t squared. So we'll have 2t plus 1/3 t cubed. So when t is 2, we'll have 4 plus, this will be 8/3. And then when t is 0, these are both 0. Well, 4 is equal to 12/3, so that'll be 20/3. So the work is 20/3. Let's take a look at the given path in this force field. So here we see the force field, and the path we're taking is from this point here to the point 2, 2. Now notice how the vector field is moving counterclockwise, and the path is also moving counterclockwise. And that's the reason why the work is positive. If the motion is in the same direction as the force field, the work will be positive. And if it's in the opposite direction of the force field, the work should be negative. Now notice for this example, our force field was 2-dimensional, and now we'll take a look at one that's 3-dimensional. So it's the same question, but now we have a 3-dimensional force field, and our path is now a space curve rather than a plane curve. But the process will be exactly the same, and for this example, we already have r of t as well as the interval for t, so we can go ahead and set up our def integral in terms of t. The limits of integration will be from 0 to pi. We're going to rewrite the given force field as a function of t using x of t, y of t, and z of t. So the x component is equal to x, that'll be 2 cosine t. The y component will be y, so it's still sine t. And the z component is the opposite of z, so that'll be negative t. And we'll dot this with r prime of t. So we'll have negative 2 sine t cosine t and 1. So we'll have negative 4 cosine t sine t plus cosine t sine t minus t. Let's go ahead and combine our like terms. We have negative 3 cosine t sine t minus t. And let's go ahead and finish this on the next page. And to integrate this, let's go ahead and let u equal cosine t. So differential u is going to be negative sine t dt. Notice we do have a factor of negative sine t dt. So this just simplifies to 3u. So we'll have 3 times u squared over 2, or 3 halves cosine t squared. Then we'll have minus t squared over 2. First evaluate this at pi. Well, cosine pi is equal to negative 1. Negative 1 squared is 1. So we'll have 3 halves, then minus pi squared over 2. And then when t is 0, cosine 0 is 1. 1 squared is 1 times 3 halves. And then minus 0. So the 3 halves simplify out, and we're left with negative pi squared over 2 as the work performed by this vector field. Let's take a look at a graph of this. So here's our three-dimensional vector field in blue, or our force field. And then in red you can see the path through space. So as a particle moves along this path from here to here, it's moving against the force field, and that's why the work has a negative value this time. That'll do it for this video. Thank you for watching.